I gave a lecture at Karachi University, a Bakery institution, and that was probably the first time that I gave a scientific talk in Karachi. Uh, what I would like to share with you today is a very exciting field that is emerging. And what I notice is that this place is going to be a major center in this area, and this is the field of what I would like to call quantum technology. It has several aspects to it, but it's a very wide field, and I would like to sort of point out how it has emerged as a major area. So let me start by telling you something. Something happened in 2018. A paper was published, a very technical paper was published in a scientific journal, Physical Review Letters, which is a very prestigious journal. Typically, when scientific papers are published, scientific journals, they are only accessible to the scientific community. Uh, People outside scientific community typically do not take notice of these publications. But this paper had an international impact. And this paper was based on an experiment which was done in China, as a matter of fact, between China and Austria. This was satellite relayed intercontinental quantum network. What it was a communication channel between China and Austria and within China. I mean, within China over a distance of 2,500 kilometers, and in China and Austria, 7,600 kilometers. The significance of this experiment was that they were able to exchange information. They did it in the form of pictures, but it could be any other message as well. It was done in such a way that if it was almost perfectly secure. If anybody tried to intercept this communication, they would have found out. I mean, after all, the signal from China to Austria, that was the problem between several countries, could be adverse countries like Russia and Bulgaria and Romania and so on. But if anybody tried to intercept or tried to find out, eavesdrop, they would find out. It was basically done through satellite, and the person responsible for it was Jian Weipan in China, and Anton Zeilinger, who won the Nobel Prize in 2022, 3 years ago. Uh, and as a matter of fact, Jian Weipan happens to be, I mean, now he's a national hero in China. There are like 9 or 10 national heroes of China, and he's one of them, mainly for this work. And once I had an opportunity of meeting with him, and I pointed out that if three words get together, satellite, secure communication, and China, people notice all over the world, especially in the United States. So what happened was that in 2018, that was the term when President Trump, his first term, and he immediately, I mean by December, he initiated an initiative of $1.2 billion in quantum technology. And the motivation is given here. He talked about quantum computers, leveraging exotic phenomena from quantum physics to computing, and also highly secure communication, the thing I talked about. And basically, the whole initiative came from this development from China. Immediately after this initiative was announced by President Trump, European Union came up with their initiative of 1.1 billion euros. And this was not all. I mean, there were initiatives in Japan, Korea, all over the world, including Pakistan. And what I hear is that in Pakistan, again, in billions of rupees here, not billions of dollars, but billions of rupees initiative has been taken, and what I learned that one of the centers for that initiative happens to be NED. So it's my great pleasure to be here. Okay, soon after this initiative was announced, the Physical American Physical Society (APS) basically came up with this idea that this quantum technology, they perceived that this quantum technology is a major initiative. It is this wave of future, and somehow it should be recognized as such. And they came up with this notion that quantum mechanics, which is considered a very specialized topic, should really move into a much at a much lower level. I mean, the literacy in quantum mechanics should be promoted. Uh, I mean, one thing I should point out is that this article was written by three persons. Irfan Siddiqui, who is again a good friend of ours from Berkeley, and I just learned that he has been to this university as well. But to me, the names are not so important as the institutions. So the first author, Irfan, he's from University of California at Berkeley, from its university, and the second author, he's from IBM industry, and the third one is from this Quantum Economic Development Consortium from the government. So essentially, these three pillars of the society were coming up with this notion that quantum should be promoted for all the people. Perhaps I should wait for a few minutes. While they are settling down, I should mention that it was such a great pleasure visiting the laboratories in the field of quantum information, quantum communication this morning, and it was certainly a bit of a surprise and a very pleasant surprise that this important field is being taken so seriously in a place like Haiti. Okay, so the upshot of this article and this thinking was that if this technology is going to touch the lives of millions, then quantum mechanics must transition beyond a specialized physics course, which it is, to a core requirement, in the sense that it should really be taught or understood at a much lower level, just like Newtonian mechanics is understood. It is expected that we would have some nodding acquaintance with the ideas of Newtonian mechanics for everyone, essentially. Well, it seems like it was okay. So this was happening in 2018, but as I mentioned, half jokingly, that I was ahead in this game from in the sense that in 2017, 1 year before this work appeared, I realized that quantum technology, quantum information is going to be a major development, and I decided to offer a course on quantum mechanics at the freshman level, for those students who just came out of the high school. And typically in my university, you can offer specialized courses, but it has to be approved by a committee. And typically this is a very sleepy committee. Whatever is proposed to them, they just approve it, mostly through email. But in this case, they unanimously rejected my proposal, basically telling me that Dr. Zubairy, you just don't know the low mathematical and physics background of the incoming students. So it is not going to work. But anyway, it's a long story. I convinced them that I could offer this course, and it turned out to be such a success that next year it was adopted as a regular course. So now the physics majors are required to take this course. And then 1 year later, again at the insistence of some faculty members, I wrote a textbook which I gave as a gift, and it's here. And the whole idea was to introduce not only the basic ideas of quantum mechanics, how strange these ideas are, but how how useful they are in the areas of quantum technology. And basically, it consisted of three sections. One was discussing the fundamentals of quantum mechanics, and then talking about, yeah, this is the book that came out. And then in this course, I talk about quantum communication, something I will talk about in this in this lecture as well, and then quantum computing. And this course was entirely algebra-based because I assumed no knowledge of calculus or any advanced ideas of mathematics from them. And it turns out that really, you could cover a lot of materials. I mean, it was quite a surprise for many people. This was a unique course anywhere in the world. I mean, at the freshman level, quantum mechanics is never ever taught. I mean, it is taught at what the United States system would correspond to a junior level. Okay, because anyway, so this was sort of my contribution in the sense that I was ahead of this game. Uh, uh, Basically, this whole notion of quantum technology that was initiated through these developments happening in 2018 uh, through this financial commitment and this idea that quantum should transition to a common a core curriculum. Basically, it is divided into typically three parts: quantum communication, quantum computing, and quantum sensing and imaging. Today, I would perhaps like to give some ideas about quantum communication and quantum computing. Quantum sensing and imaging, I have devoted many, many years working on in these areas, but today perhaps there will not be enough time to get into that. So let me start by talking about quantum communication, what it is, and how it is different from the conventional communication channel. Quantum communication, the advantage of quantum communication is to take advantage of some very strange behavior of quantum systems, taking that advantage from there to accomplish something which conventional communication cannot accomplish. And that is that you can communicate completely in a secure manner between two bodies, like these Chinese experiment. Uh, Secure communication has a long history, thousands of years. As a matter of fact, just to give you an idea, that thousands of years ago, how this secure communication was done, and the way it was done was that you would sort of exchange some message in a garbled form. I mean, this does not mean anything. But what has happened is that in this case, it is an encoded message with a certain key. And here I've chosen a very simple key by just replacing one letter. A becomes Z and B becomes A, etc., etc. And once you do that, then J becomes I and B becomes A and N becomes M. And then the proper message is received. The key to this kind of communication was an exchange of this key. I mean, this is a very simple one. Of course, you can make much more complicated keys. The major thing about it was the security of the key. This key should be exchanged in a very secure manner, such that this key is known only to the sender and the receiver, and nobody else should have access to it. So this is how it was, and this essentially this notion of cryptography uh, stayed with us for almost 2,000 years, until almost to 1970. There was no other way of communication except some sophisticated version of this. But this protocol, this kind of secure communication had a couple of very serious problems. One of them was that this key has to be exchanged through secure channels. What in ancient times meant that you and I get together, exchange the key, then you go to your destination and I go to my destination, and maybe through some intermediaries we communicate. But as you can imagine, very tough job. The second problem was that a clever eavesdropper, by getting this information about this garbled message, can construct the full message and can, in some sense, find out what the key is without the sender and the receiver realizing that. So the sender and receiver may think that their key is secure, but actually it is not, because somebody has worked it out. And as we know that in financial dealings and in military applications, and this is very important, that the security of the key is maintained. So these are the problems. Well, it turned out that in 1970, and this is an incredible coincidence, that was essentially the time when internet was coming in our lives. And that was also the time when three scientists, three mathematicians, Rivest, Shamir, and Alderman, they came up with a protocol for secure communication in such a way that the key was to be exchanged on what we call public channel. Now, this seems like a contradiction in terms. How can we exchange key on a channel which is accessible to everyone, including our enemies? But this is what they did. And the thing about this protocol was sender and receiver exchange key on public channel. So I could pick up a telephone and communicate the key, and this telephone line could be compromised. Still, the communication was secure. But the disadvantage was that the ultimate security was not guaranteed. It was very, very difficult, but not impossible. So this is the situation which persisted from 1970 until almost today. This has allowed this e-commerce to exist. The reason why we are able to send our credit card information to purchase anything on through our cell phone has to do with the fact that this RSA is very secure. And here the key has been exchanged through public channel. But again, as I say, ultimate security is not guaranteed. So the question that came up was, can we have a protocol where the key is exchanged on a public channel, these fiber optics lines, or like these Chinese and Austrians did through transmission through atmosphere? Can one exchange key on a public channel and in such a way that if there is an eavesdropper, the eavesdropper should be identified? Now it looks almost impossible. You need perhaps magic to do that, but of course we don't know magic, but we know quantum mechanics. So quantum mechanics can do something like this. And this is what I would like to explain to you in a minute, how these very simple ideas, very, very simple ideas can accomplish this almost impossible task. So let me just give you an idea that, first of all, the information today, when I say I'm happy to be here, is typically not transmitted in the form of these English letters, E, A, B, C, D, etc. It is always done in terms of numbers. So just to give you an idea, for example, here I have listed the numbers 0, 1, 2, and so on. The small letters A, B, C, capital letters A, B, C, alphabets, and so on. And these are all represented by 8 binary bits. So the whole information system that continues today and for last several decades and that is that information is sent in these binary numbers. So, for example, if I want to send the word book with B in capital, then I just go back to this representation and represent B by those eight sequence of these zeros and ones, and small a with this other sequence, and so on. So essentially, it is the sequence of zeros and ones which we want to transmit. So a secure way of sending these numbers would ensure the security of communication. The typical protocol works something like this, that communication between Alice and Bob is such that Alice wants to send a binary message in terms of this sequence of zeros and ones. And then there is a key which is common to both Alice and Bob, and you add this message to the key and ones, which is what you send to Bob. And then Bob applies the key and recover the message. So, so this is how most of the communication today works. Actually, almost all communication works fundamentally along these lines. For the security purposes, as you can imagine, the critical point is the security of the key, the sequence of numbers, or binary numbers, 0 and 1s. If we can somehow secure, in a secure manner, exchange it between Alice and Bob, the sender and the receiver, then we are okay. And this is really the whole idea. Well, in order to, the way it is implemented, and it was implemented in this experiment which I mentioned at the very beginning of this talk, this big experiment through satellite, essentially uses a property of light. Light, we treated light consisting of photons, particles. And these photons have a property called polarization. I mean, if you want to be more precise, then what is happening here is that, light consists of what we call electromagnetic waves. This is electric field, magnetic field, which is oscillating. And the direction of the electric field defines the direction of polarization. So this is the characteristics, and we just use the property, this property, polarization property of the photon to accomplish this impossible task of communicating, of exchanging key on a public channel in such a way that if there is an eavesdropper, that will be traced. So this is how it is done. So let's see. The only thing that we need to know is this core principle of complementarity. Those of you who were there in my talk yesterday would recall this principle that we talked about. And essentially what it says is that two observables are complementary if precise knowledge of one of them implies that all possible outcomes of measuring the other one are equally possible. Very heavy language. Okay. So let's consider an example, a very layman example to understand this whole idea. The idea is basically goes something like this: that supposing we have these two kind of mutually perpendicular doors. So, for example, supposing I have a situation where a door is in this direction and in this direction. If I'm walking through this door in this posture, then of course I'll pass through this door, through this door. If I'm lying down and then moving in a direction, then I will pass through this door, horizontal door. So there is no confusion there. But what happens if, standing like this, I encounter two doors, one in this direction and the other one at 45 degrees? Now what happens? So you will think, and you will now talk in the language of probability. You would say 50% probability that you will go through this door and 50% through the other door. This is all that we need to know in order to understand this, one of the most important protocols of our lifetime. Just this knowledge. So essentially what we say is that the polarization is measured in this way, what we call basis, and this is a mathematical term, and this circle represents a plus sign there, which is a symbol to say that there are two doors which are horizontal and vertical. And then there is this other basis which I call X basis, and this means there are two doors which are like 45 degree and 135 degree. So what happens is that I mean, this quantum cryptography is essentially based on just this notion. And the way it works is like this: that if we have these two bases, this plus basis which corresponds to horizontal axis 0 degree, and vertical basis 90 degree, and x basis means 45 degrees and 135 degrees. Lower angle corresponds to a logic 0, higher angle corresponds to a beta 1. Okay. And on this basis, we can predict what happens if different polarizations are sent in. So let me, if you can pay some attention. I mean, if this is understood, then this whole idea is almost trivial. So for example, if I have polarization in this direction, and this what we call a beam splitter having these two directions for polarization. So since it is in this, so these are like doors, horizontal and vertical door. So in this case, the output will be vertical because it can pass through this door. If on the other hand, I have polarization in this vertical direction, but the doors are in this X configuration, then there is no well-defined prediction. It could be this or this. Similarly, if it is horizontal, then it will come out horizontal. If it is horizontal, but this is X configuration, then I can get either X or 135 degrees, 145 degrees, 135 degrees. So you can construct this whole table based on that. And this is all that we need to know. Okay, so let's see how this protocol is done. So what happens is that now let's keep the objective in mind. Alice and Bob want to create a sequence of zeros and ones, random sequence of zeros and ones, in such a way that no eavesdropper can access to it. So in this case, what happens is that Alice sends a photon with using these kind of polarizers, and what happens is that here it could be horizontal 0, it could be 90 degrees, it could be 45 degrees, 135 degrees, and so on. So in vertical, in this plus sign one, we can have either 0, horizontal, or vertical, 90 degrees. And in X, we can have 45 degree or 135 degree. So this is now the polarization of the photon, which these different photons, which is chosen by Alice. And they correspond to this sequence, zeros and ones. 0 degree and 45 degree correspond to a 0, and 90 degree and 135 degree correspond to 1. So now these stream of photons are now traveling through some public channel, like in the Chinese experiment through atmosphere, in conventional channel through some fiber optics cables to the receiver. Now receiver doesn't know what Alice has chosen. So the receiver would choose different bases to measure what polarization is. So there, where somehow it happens that the basis plus or X, they match between Alice and Bob, then Bob will get the same outcome that Alice sent. Because if it was in this direction, and if the door for the Bob is open in this direction, then of course it will go through this direction. But if it is going in this direction and Bob's door are 45 degree, 135 degree, then it doesn't know which way to go, so it can go this way or that way. So we can see that in this case the outcome will be that this matches, so therefore horizontally polarized. This one does not match, so therefore it could be 45 degree or 135 degree, doesn't, and so on. So this is how it is. And now at this point, Alice and Bob basically communicate on what we call a public channel. And they compare what basis they had chosen. They do not compare what the outcome was, but they compare this basis, and where they match, they decide to keep it. And where they see that they are not matching with each other, that they drop. So here they will keep the first one, the fourth one, the sixth one, and the ninth one. Okay? And that gives them this key. So this is now the random key they have generated. So this is the protocol which is used. This is the protocol which was, for example, realized in this very famous experiment from in China. This protocol, I mean, as a matter of fact, we can show very simply. Perhaps I will not go in some details, but it can be shown that this is perfectly secure. I mean, if there is an eavesdropper, using this kind of logic, one can find out whether there is somebody who is trying to listen. Because listening in quantum systems, measurement disturbs the system. And if somebody is trying to measure, the system is disturbed. This is not common with the classical type system. If you want to observe whether it is like this or it is like this, you can measure it, and it is not disturbed. It will remain in this either in this position or this position. Not true for the quantum system, and that is basically used for the purpose of security. So this is how it was done. So it is impossible for an eavesdropper to find the key, and if she tries to do it, then both sender and receiver will find out. So this is amazing. So it is a completely secure system, and such a secure, it is with such a security that it is sort of it is it has really attracted attention in the political circles all over the world, because this is the wave of the future. And now we can see, this experiment. This is Jian Wei Pan. He, as I mentioned, he is now a national hero to the extent that 2 or 3 years ago there was a conference in Brazil, and those of us who went to that conference, who were invited to lecture there, when we came back, we were debriefed about what transpired between us and Jian Wei Pan. So he's really considered like a national security risk or whatever you can call it. Okay, so this is about one aspect of quantum communication. And this has been around for a while. I got involved in quantum communication much later, in around 2012, 2013. And now I'll shift to a protocol that actually we developed, and that is also like a magic. I mean, it is such a counterintuitive result that we came up with that many people in the scientific community refuse to believe us. And there is a long story of what transpired in this situation. But eventually now, I think everybody, not I think, but even our detectors agree that we were right all along. Okay, so what it is that is so counterintuitive. So this is a work which was done in my group. The first name, Saleh, was a student. Chen Li was from China, but he was my postdoc at that time. And Amri was my guest at that time. So we published this work in 2013, about 12 years ago. The whole idea here is this. So this is just the generic system that I'm talking about. The whole idea is this, that there is Alice. Alice has a source of photon and some optics inside this box. And I'll show you in a minute what kind of optics, some very generic optics, something which perhaps exists in the lab here as well. Alice has two detectors for photons, D1 and D2. Bob, on the other hand, is far away, could be very far away, and Bob has only a mirror. And Bob So the photon is sent by Alice through this optical system, and what Bob can do is either block by just putting his hand in front of the mirror or not doing that, like in this last configuration. And what happens is that if Bob decides to block, then it happens that this detector clicks, D1 clicks. So Alice knows that Bob blocked, and which may mean that he wanted to send a 0. If Bob does not block, let the photon come and get reflected, then the click is at D2. So now Alice knows that Bob wanted to send the A1, for example. And so far no magic. But the magic is that in both these situations, there is no photon or nothing between Alice and Bob. In this transmission channel, there is absolutely nothing. So somehow the photon bounces back and forth in here, but it senses what is happening at Bob, whether Bob put his hand in front or not, nothing, or nothing in front. So there is no photon or nothing, as a matter of fact, within this public channel. Still, one can have a communication between Alice and Bob. And this is something like psychic communication. Of course, it is not, but it is psychic communication. As a matter of fact, once this work was published, a newspaper was interviewing me about it, and I mentioned this fact that this work is something like psychic communication, and then they made it a headline out of it. And for several months, if you Googled psychic communication, my name would come near the top. So I was associated with this. Okay, so in this case, we have a direct communication channel between Bob and Alice, and no photon in the transmission channel. How is it possible? And people really refuse to believe. Some very, very eminent scientists refuse to believe that this is even possible. Because for thousands of years, what we have believed in is that if we want to have a communication, we should have an exchange of something. Okay? Either molecules vibrating all the way to your eardrums, or in optics, these light particles, photons that are basically exchanged, and so on. So electrical signal, etc. Okay? But the idea that there is absolutely nothing that really goes against our intuition, and that is what happened with many people. Okay, so this is, I would not go into any details, but just to indicate that this box that I showed you has these very generic optical instruments, which are available in almost any optics lab around the world. Here we have mirrors, photons. This is the photon source, generating single photons, and polarizing beam splitters. These are which select what polarization has to be chosen, and some switchable mirrors. Switchable mirrors. Basically, switchable mirror is like a door. It allows the photon to come in, and once it is in, you can close the door, and then it just bounces back and forth. And when you want this photon to leave, you can open the door. So here, the person is like photon, and the door is like this polarizing switchable mirror, and so on. So ordinary mirrors and optical delay lines and so on. So this is those who are working in optics labs would know are very generic, very ordinary kind of optics, but this is available. Okay, if I try to explain it this way, it would be really very, very confusing. We will all get tired very quickly and so on. But as a matter of fact, there is a way to understand it, and that understanding can be almost trivial, really, very, very simple. And one message of this talk and one message of this whole field is how we can accomplish big, huge tasks with some very simple physics ideas. So here, this is no exception. So here, I mean, I mentioned a very, perhaps the simplest optical system in quantum science, and that is that if I have, for example, a single photon coming here and no photon here, and there is some kind of a beam splitter, then there are two possibilities. This photon can get reflected or it can get transmitted. This can happen with 50-50 probability. So it is a probabilistic event. That is all. It turns out this is all that you need to know in order to understand this protocol that we developed. Nothing more, which is astounding. Uh, so here I mentioned that if I, instead of a single beam splitter, I have two beam splitters and two mirrors. Then what can happen is that this photon can either get reflected, come here, and then get reflected or transmitted. And the other possibility is it can get transmitted and then get reflected here and then reflected or transmitted. It turns out that in one of these paths, it can have a destructive interference, so no detection at D1, and it will D2 will click all the time. So this is, I mean, now what I'm doing right now is not telling you the protocol, just setting you up for understanding of that protocol. So this is a very simple system of beam splitters. There's other possibilities that on this side I put an object. So this photon, if it is transmitted, it will be absorbed, but otherwise it will go through here and come back and then give us a click at D1 and D2 with equal probability. So basically this is what we get. In this case, we will get a click at D2 with definiteness, with 100% probability. In this case, 50% probability is that it will be transmitted, get absorbed by this object, but there is a 50% probability that it will come in here and give us a click at D1 and D2 with equal probability. Trivial. But now, even in this very, very simple system, there is a big mystery there. And the mystery is this, that if we want to detect an object, like you see this object in my hand, how? The way it works is that this light, which is coming from there, comes in here, strikes, and then reflects into your eyes, and you detect it. If somebody tells you that you can detect this object without why I get very distracted when people are moving. I lose my chain of thoughts. So I wish you have a door in the back, in the behind rather than in front. So in this case, what was I saying? Yeah. So the thing which you would consider deemed impossible is that you detect this object without this light ever striking. There is no way. I mean, basically, it is this light which strikes here and then goes into your eyes, and that is how you detect it. But if you look at this system rather carefully, this is precisely what is happening. In those events where you get a click at D2, the object would be here or not here, you would not find out. Basically, there is a D2 click here with 100% probability, but there is a D2 click here as well with some probability. So, no difference. But please notice that in those events when D1 clicks, then it has to be this. It cannot be this, because here there is no possibility that D1 will click. But here, when for those events, for those some events where D1 clicks, in that case it is this event, but in this event corresponds to an object existing here. But of course, this photon, there is only one photon. This photon would not be on this side. it has to follow this trajectory. It should come, get reflected, come here, and then give us a click at D1. So in this case, this D1 clicks indicates to us that the object exists here, but the photon does not hit the object. So here we are observing an object without light being scattered from it. So we are seeing an object without actually seeing it, which is quite, and this is what is referred to as interaction field measurement. And these ideas actually came through this work of Eliza and Whiteman. Whiteman became my detractor for several years later. It's a whole story in itself, but he came up with this idea, interaction field measurement, in 1993. Remember the date. Okay, now we make the system more complicated. But complication means that we add these beam splitters, many of them. Okay, and these are just the mirror symbol. It turns out that in this situation, when there is no blockade here, you get a click here definitely with 100% probability. In these events, when you block at each level, so instead of putting your hand, you put your arm in front of these mirrors, then you get a click almost always at D1. So this is something which we can prove by just considering that one beam splitter and applying it many, many times and get this result. And this result again was obtained around that time, and this was realized in 1995 by an experiment which I don't add a slide here, by the group of Zeilinger, Anton Zeilinger in Austria, for which he won the Nobel Prize 3 years ago. Okay, now let me come to what we did. So we basically considered applied it to communication almost 20 years after this first ideas came out in 2013. And what we argued was that let's make the system more complicated. See, we started with one beam splitter, then we had this array of beam splitters, with two beam splitters, then we had this array of beam splitters. Now we had a double array of beam splitters. So this is now our protocol, such that on this side we have the same thing, just a mirror to reflect. But on this side we had this whole array of these beam splitters. And the way we set up our protocol was such that all these, the photon source, the beam splitters, these mirrors, these beam splitters, these mirrors, everything belongs to Alice. What Bob has is just this array of beam splitters. And between Bob and Alice is the public channel. You can make it as large as you like. Here it is shown a very narrow region. Now let's see what happens. So Bob has two choices. One of them is he does not block, which is the situation here. And this might correspond to, let's say, allergic zero, which Bob wants to set. So in this case, what happens is that the photon will basically follow either this trajectory or it will be transmitted here. And in that case, it will hit this configuration. But this configuration is this configuration. And the photon will be definitely detected here, and be lost. So in this case, this whole thing, in some sense, acts like an absorber, like here. And in this case, just like here, you will get a click with almost unit probability at D1. But please notice that in this case, the photon could not exist in the public channel. Because if it existed in the public channel, then it would end up here. There is only one photon. It's not an array of photons, just one photon. So if it is on this side, it will be detected at DL and be lost. So if I get a click at D1, then, or Alice gets a click at D1, the photon would not exist in the public channel. So, and still Alice can find out what Bob was trying to do. Now let's consider the situation when Bob decides to block, puts his arm in front. This is a simple configuration. As I mentioned, this complicated kind of circuit would typically what we would do in the lab. But in this case, this situation is something like this. And in this case, what happens is that the photon almost unit probability goes on the other side. So this whole situation acts something like this, and we get a click at T2. But please notice that in this case also, the photon would not be in the public channel. And still, a click at T2 indicates that Bob decided to block. Bob decides to send a logic 1. So now we have a situation where Bob can decide to send a 0 by not blocking, or send a 1 with blocking at every stage. And in both cases, you can see there was no photon in the public channel. Very simple argument. Very simple system if you look at it this way. So just this very simple idea can lead to something which is almost mind-boggling, something which we have lived in for 2,000 years or more, and now we are showing for the first time that you can have a exchange of information through a channel where there is no photon. Nothing exists in there. And in 2014, I was making this presentation at a conference, and Zeilinger was in the audience. And he had done the experiments, which I unfortunately missed the slide. He had done the experiments on interaction-free measurements, for which that was part of his Nobel citation when he won the Nobel Prize. And he literally held his hand like this, and he said, "Why didn't we think of it? It took 20 years for us to realize." So now, I mean, this whole circuit, so I mean, it's very easy to understand this circuit. But if you want to do an experiment, this is what perhaps you would do. So this is something, and it turns out that this work really created a lot of discussion. And Weidmann led the effort of interaction-free measurement. He led the effort to really show that what we are saying was not right. And that went on for many years in print. He would write a comment, we reply, and we would hit upon what he did and so on. So this went on until his boss. And Weidmann was a student of Aharonov, Yakir Aharonov. And Yakir Aharonov, if today you ask a number of physicists, who is the greatest living physicist today? I think 20% would reply Yakir Aharonov. Okay. So Yakir Aharonov eventually wrote a paper with Grundig in which he made this statement. I mean, he talked about our paper. This describes a remarkable effect which they call counterfactual quantum communication, transmission across a transmission channel of information from a sender to a receiver without any physical particle traveling between them. For all our familiarity with quantum non-locality, this is entanglement, those of you who are familiar with it. The effect is startling. It involves neither non-local quantum correlations, which anyway do not transmit information, nor the relative phase of Aharonov-Bohm effect. This is what Aharonov is known for, and this is what Aharonov is saying about his own work, that nor the relative phase of Aharonov-Bohm effect. If any effect evokes Einstein's famous phrase, spooky action at a distance. Those of you who have taken a course in quantum mechanics would know what I'm talking about. Einstein was so dissatisfied with quantum mechanics that he talked in this language, spooky action at a distance. So basically what they are saying is that any effect evokes Einstein's famous phrase, spooky action at a distance, it is this one. So this was really a vindication of our work. And this work, as a matter of fact, was the experiment was done, and the experiment was done by none other than Jianbai Pan. And there is a background of it. I mean, this paper was published in 2017. In 2013, I turned 60. I turned 60. There was a conference held in Beijing, to celebrate that occasion. People from many different countries came there, including Jianbai Pan. And Jeremy Bond at that time was assigned to do this experiment through the satellite. And he was a very nervous person at that time because he was not sure. The Chinese government had given him at that time $300 million. And Jeremy Bond's attitude was that if that experiment fails, he should have at least something else to show for it. And he wanted to discuss with me our protocol, whether he could implement that in case his, his major objective is not realized, at least he will have something to show for it. And as a matter of fact, he did it. He did this experiment and it became very well known. It was published in 2017. And this work, our work got a lot of publicity, even Wall Street Journal talking about this researcher at Texas A&M University doing an almost psychic photonless communication. And in physics today, which is the mouthpiece of the physicists around the world, there was this very colorful title and the story, and it basically talked about this work. I mean, basically it says it is difficult to grasp the implications of an experiment that seemingly sent data from Bob to Alice without any physical messenger passing between them. And he mentions that this work was done in 2013 at Texas A&M University by our group, and then point out that it was joined by Pan and his colleagues who verified our predictions. So this was. Okay. So this is first part of my talk, talking about quantum communication. But now I would like to go to the second leg of this quantum technology revolution, quantum computing. How much time do I have?
We have around 15-20 minutes. At least 15-20 minutes.
Okay, very good, very good. Okay, so let me now switch gears and now talk about quantum communication and quantum computation. And let me first give you the history of it. And actually, the very first ideas about quantum communication came in 1982 through the work of Richard Feynman, who is one of the premier scientists of our generation. He passed away in the late 80s, but he was the one who started the ball rolling. And he talked about this potential of quantum computer and simulation of quantum mechanical objects by other quantum systems. The very first presentation he gave was in 1983 at a conference in Manheim, California, and I was there. So I always claim that I was there at, when the birth of quantum computing took place, because that was the moment. But at that moment, I realized, I listened to Feynman's talk and could not really appreciate what significant thing he was talking about. Not hardly anybody realized that. Only very handful people could really see through that these very fundamental ideas could lead to something like a whole field in itself. The first person to put it on a sound ground, that was David Deutsch at Oxford University in 1985, who described a universal quantum computer. If I had to give a full-fledged lecture, I would have described to you what we mean by a universal quantum computer. But really, the field took off. I mean, it was like going like this, and then suddenly it took off in 1995. And this was through the work of Peter Shor, who showed how to factorize a large number, a product of two prime numbers, a very large number, which is product of two prime numbers, and how we can solve that problem, how we can find out those factors in a very efficient manner. Now, you might think big deal? I mean, this is a highly mathematical problem. What is the significance of that? You know, I mean, that if somebody could factorize a large number into its prime factors, what is the big deal? But it comes out that it is really very, very big deal because if you can factorize a large number into factor very easily, then all this e-commerce will just disappear. You will not be able to send your credit card number through your cell phone to buy anything. It's as simple as that. This is the foundation of RSA, which I talked about in the beginning, that how this communication can take place in a secure manner. But then came another protocol, and this was by Love Grover, and he basically talked about just around that time, and he talked about searching an object in an unsorted database. What does it mean? Let's imagine a telephone book, which are completely out of fashion. So maybe the younger people would not know what a telephone book is, but in my time, it was the major thing in every house and every office. So what is in a telephone book? You have these names and your telephone numbers. So the way we use the telephone book is that if you want to find my telephone number, Zubairy, last name Zubairy, then what you will do is that you will immediately jump to Z, and in Z you will search for a U, and then B and so on, and you will find out the telephone number within seconds. So this is a sorted database. But let's consider the reverse problem. Somebody gives you a telephone number, and now you have to find out whose telephone number it is using the telephone book. Now you have to really, I mean, there is no way except you have to start, from A to B to C and so on, so on. If you're lucky, if the name happens to be Abdul Salam, then you're lucky on the first or second page the number exists. But if the person's name is Zubairy, then you have to go almost to the last page to find out the telephone number. So on the average, it would take how many people there are. So for example, you go to a big city like Karachi. Okay, so there are a million telephones, for example. And so roughly speaking, it would take on the average 500,000 searches to get to find out whose telephone number it is, unsorted database. But it turns out that in quantum computing, in some special situations, you can do this search in what we call square root of n. So if it is million long list, you can sort of, in some special situations right now, you can actually find it in only 1,000 steps with good accuracy. So this is the power of quantum computing. With these two protocols, the field literally took off. I still remember in the summer of 1995, I happened to be in Germany, and I literally worked day and night to learn everything that was known at that time about quantum computing. Because at that time, everybody realized that this is now going to be the field of the future because of this interest. So this is sort of a brief history, and this revolution continues to this day. Not so successfully. I mean, if somebody asks me at the end my opinion, I will give you my very honest opinion. But let's wait for that moment. So now the question is, what is quantum computing? How is quantum computer different from this computer? So the basic difference is that all these computers, like this one, they are using, I mean, it is based on, I mean, it is made up of semiconductors, and those are quantum materials. You cannot discuss the properties of semiconductors using Newtonian mechanics. You have to know quantum mechanics to understand that. But the operating features, those are classical, in the sense that the zeros and ones, which form the backbone of the computer, they are classical objects. They could be voltages. A voltage up corresponds to a 1, voltage down may correspond to 0. Okay? So you can have a voltage up or you can have voltage down. A quantum computer, on the other hand, is based on quantum bits, quantum states. And those are denoted in this very funny notation, 0 and 1. And what these are in the laboratory, something like photon number, either one photon or no photon. It can correspond to this polarization that we talked about, vertical polarization or horizontal polarization. Vertical corresponds to a 1 and so on. Electronic spin up, 0, 1, spin down, 0, and so on. So there are many different energy levels in an atomic system. So these represent the bits in a quantum computer, the quantum devices. And the question is, what does it do for us? Why we use these quantum bits? What is the advantage? And we are going to see tremendous advantage. So basically, when we ask this question, why quantum computer? Then we say, well, quantum. I mean, the very interesting property of a quantum system is that you can have it in a coherent superposition of two states. Classically, the system can be either up, voltage up, or voltage down. Quantum mechanically, system could be simultaneously in up state and down state, which is a very novel feature of quantum mechanics. So the advantage is that we can have a superposition state like this simultaneously in these two states, such that if we measure, we make a measurement, then we get this result or this result with the corresponding probability. The other important thing is that we can have this quantum entanglement. This is a very amazing feature which is really special to quantum mechanics. And what it is that, I mean, classically, if I have two objects, then whatever I do to this object will not affect what is happening here. Not at all. I can crush it, I can throw it, I can rotate it, and so on. But in quantum systems, we can prepare a system something like this, such that if it is 0, then the second system is in one state and vice versa. Now, at this point, if you want to find out what is the state of the first system, you cannot find out. What you know is that if it is found in this state, then the second particle has this state and vice versa. And so in this case, the two systems are not independent of each other. You cannot treat them independently. They influence each other. This is what is referred to as an entangled state. And you can have multi-particle entangled state. So now let's try to understand how this helps with quantum computing. So let me give you the example of a window. So the window can be, if it is one window, it can be either open or shut. It can be 0 or 1. Open, 1 and shut, 0. So it can have, if I have two windows, then I can have 4 possibilities. Both of them could be open. This one is open, this one is closed, this one is open, this one is closed, and both of them are closed. There are 4 possibilities. If I have 3 windows, then it will be 2 times 2 times 2, 8 possibilities. And if I have 1,000 windows, and there are buildings which have 1,000 windows, then the number of possibilities will be 2 raised power 1,000. 2 times 2, 2 times 2 times 2, 2 raised power 1,000. So these many possibilities for the windows. Now you might think, well, it's okay, it's few choices, but it actually turns out that this number happens to be much larger, not much, but larger than this number, 10 raised power 256, 10 times 10 times 10, 256 times. It turns out that this number is so large. This corresponds to the number of atoms all the atoms in this entire universe. So it turns out that there are these are the number of possibilities. If you have only 1,000 windows, there are these many possibilities. So it's a huge, huge number. Now let's come back from windows to atoms. Let's consider just 1,000 atoms. And these 1,000 atoms could exist on the tip of a needle. It's a very, it's a very, very small number. These 1,000 atoms can store information equivalent to all the atoms in the entire universe. So we can have 1,000 lasers to manipulate these 1,000 atoms and build a computer for which to do a calculation for which we would need we would have a computer like this based on every single atom in the entire universe. This is a very, very powerful statement. This was the statement which Feynman was making at that talk, which I mentioned, and I'm California. So this is the potential that now you can build a computer with just 1,000 atoms, and if you do your manipulations right, then you can accomplish a task which for which you would require every single atom in this universe on this computer. So quantum systems can do more magic. So you might say, well, this is wonderful, but why there is no quantum computer till today? Okay, so now that is an obvious question. Feynman was talking about in 1982, quantum mechanics was invented 100 years ago, but there is no quantum computer today. So why it is? And it turns out that there are two problems. So now the good news, we can have a computer with 1,000 atoms as good as a computer with all the atoms in the entire universe. But now comes the bad news part. So this is what I mentioned that actually what it can do is so in today's problems, for example, if we take biology and we have some kind of a virus, and that basically the molecules of these viruses consist of almost thousands of atoms. And if you want to analyze them on this computer, it is impossible for the reasons that I mentioned. So a quantum computer will do this job rather straight, in principle, easily. So quantum computer can do that. But now the question is why there is no quantum computer? And now the bad news part. The bad news part is that even for a superposition, when we say that the system could be simultaneously in this state and in this state, it can be a window could be simultaneously open and closed. When we try to look at it, it is either open or closed with probability. Quantum mechanics has inbuilt this probabilistic nature. So now what we say is that if we forget about entanglement, which is much more complicated, even for the simplest system, which is in a superposition like this, simultaneously in these two states, when we try to measure this system, so we do all these calculations, all these atoms, 1,000 atoms, and we manipulate them with the help of lasers and so on. Now at the end, we have this output, and now we try to take a measurement. That is probabilistic. That is the result in this case will be either 0 or 1 with these probabilities. So now this is bad news. Now you might wonder why even we are talking about quantum computer, because from a computer we expect 2 plus 2 is equal to 4. If some computer gives us a result which says 2 plus 2 is most likely equal to 4, but it can be perhaps 5 sometimes or 3 sometimes, that computer is no good for us. So this is something which is inherent in any quantum system. So this is the bad news part. There is another bad news part. There is another bad news part, and that is this decoherence, interaction with the surroundings. So the system which we expect that this pen, this object, if I place it here, and there is no disturbance at all, no wind blowing, nothing, here, very low temperature, so there are no vibrations. I can come back after a million years, it will still be sitting here, like this, okay, if there is no disturbance. Quantum systems are not like that. An atom in an excited state is interacting with a reservoir, the rest of the surroundings. And this rest of the surroundings are much more complicated than we can ever imagine. Let me give you an example of decoherence from our regular life. Supposing I have a hot cup of coffee, hot cup of tea, for example, okay, in this room. Somebody offers me a cup of tea, this cup of tea here, okay, and do nothing. What I observe is that since this cup of tea is interacting with the rest of this room, after a while, after a few minutes, it will get cold. It will lose its energy spontaneously without my doing anything to the surrounding. But the reverse is not true. It will never happen that I have a cold cup of coffee here and somehow it absorbs energy from the surrounding and become hot suddenly. That never ever happens. So decoherence in some sense implies that any interaction with the reservoir or interaction with the surrounding basically destroys the state of the system without our intervention. And this is true with any quantum system or any system in general, but any quantum system. And you have to overcome. So the field of quantum computing at this point is at a stage where two things. First of all, you have to come up with some solution for this decoherence problem. You have to find materials and techniques and so on, where this decoherence problem can be taken over or taken care of. As a matter of fact, in my group, we have spent years trying to work on this problem, and I gave a talk in Islamabad just 2 or 3 weeks ago, talking about how one can overcome in some systems this decoherence problem. It is a very tough problem, but we showed that in some situations it can be done, not in all situations, of course. So this is a very active area of research, how to overcome decoherence. The whole idea about coherence, about quantum computing, now you can see is to come up with protocols, come up with problems, such that these problems you cannot overcome. So you can take advantage of the fact that we can entangle the states of a kind and overcome these problems. And that was the beauty of this Shor algorithm and Grover's algorithm. So this is really what is the most important area right now. Perhaps I should mention that many years ago, Grover's algorithm, how to realize that, and there was some logic gates structure, and it turns out that I and my colleagues have the patent for that. But when we try to do the same thing for Shor algorithm, it didn't work, which is much more interesting. Okay, so now let's come to the Shor's algorithm. What does it do? I cannot give the full details. Incidentally, this book that was displayed, this quantum mechanics for beginners, everything is spelled out step by step. So if you get an opportunity to look at it, I think that would be wonderful. So this is factorization of integers. So what we realize is that if I'm given some prime numbers or any numbers, and I want to find the product of it, multiply them. That's a simple problem. You can give me a 1,000-digit number multiplied by another 1,000 number and give me a piece of paper and pencil. I think by within a few hours, I can give you the answer. So that is not a very difficult task. For a computer, it is like seconds. It can do that. But the reverse problem is very, very complicated. If I give you a number which is product of two prime numbers, finding those numbers is a very difficult job. But just to give you an example, this number, which is 154-digit number, it requires 700 of these computers to solve this problem a reasonable amount of time. If I have 200-digit number, it would take almost 6 years for the fastest computer available today. If I have two 50-digit number, it would take almost 18 years. And this is what is used in RSA. So the reason why RSA is secure is because you need to, in order to break it, you need to factorize a 250-digit number, and on this fastest computer, it will take 80 years. And 80 years, the knowledge is obsolete, so you are safe. For 1,000-digit number, it would take almost a billion, 100 billion years. And just imagine that the age of the universe is supposed to be something like less than 14 billion years. So you will take many times the age of the universe to factorize a 1,000-digit number. It is so difficult. And that ensures the security of RSA, the security that we use on our cell phones and in our communication channels. So this is very important. But it turns out that Shor algorithm, this quantum computer, in principle can do this job very easily, a few billion steps, and it's done. So if a quantum computer is built to solve this particular problem tomorrow, then all our e-commerce is gone. We will not be able to use our cell phone to send any information there. But fortunately, we are a bit far away from that stage. Okay, why this problem is interesting? So this I give you a simple idea of how this RSA works. So in RSA, what happens is that supposing I want to send a key to all of you and do it on a public channel, so much so that I can put the key on my website, okay, so which everybody can see, my friends and perhaps my enemies as well. Okay. So the way it works is that I generate a number n, and which is a product of these two numbers p and q. These are prime numbers. And from these three numbers, n, p, and q, I generate two more numbers, e and d, in a prescribed manner. And this prescription, again, is given in full details in some of these books here. Well, it turns out that what I do is that I announce this n and e to all of you. That if you want to send me a message, encode your message with these two numbers, which are known to everyone, to my friends and to my enemies. So when you want to send a message, and message is a number, as I mentioned. The messages are sent in terms of numbers. You encode your message with this E and N and send back to me. So if one of you wants to send a message, some number, encode it with E and N and send to me. And I have the decoding number, D, I can find out what number you wanted to send. The amazing thing in this is that all the other friends are listening to what you sent. They also have E and N. But in order to find out what message you sent, they will have to find these factors P and Q. That is why this problem is so important. Because if somehow you could factorize this number n into its prime factors, then you can immediately find out what E is and what is D, decryption key. And using your decryption key, you can find out what the message is. So this is the essence of the significance of this quantum computer. And then finally, I show you a mention about searching of an unsorted database. This is not as dramatic as the Shor algorithm for factorizing a number, but nevertheless, historically, very, very important protocol. Okay, so this is almost like the end of my talk. Let me just mention that I gave you the history of this book, Quantum Mechanics for Beginners. So this was written in 2019. I offered the course in 2018. I proposed this course in 2017, and it has been a big success. Oxford University Press told me after 1 year that this was the most selling selling book in physics by their press. But then I thought I should write a popular book in which I explain, I convey my excitement about physics in general and about these laws that govern this universe, quantum mechanics and relativity and so on. And I wrote this book, A Mysterious Universe. And again, this turned out to be quite popular, but I realized that the applause was not from my friends in Pakistan, but from elsewhere. I mean, this book was translated, I think, in 5 or 6 languages, etc., but not in Pakistan. So, and the second thing I realized was that somehow, I mean, I've become a big champion of it, that if we want to create a scientific culture in this country, then science should be taught in the mother language, in the language that we speak. I can give a full lecture on that, and I've written a lot about it in articles and so on. So then, with that motivation, 2 or 3 years ago, when I turned 70, so I thought, well, I'm now in the real, truly twilight zone of my life. So instead of concentrating my 100% efforts into science, which I did for the last 50 years, I should do something different. And then I learned to write in Urdu, and I wrote this book, Kainat Ki Hayrat Kara. And in this book, I try to explain, the subtitle is Quantum Mechanics or Nazariya-e-Izafiyat, Einstein's Theory of Relativity से वाबस्ता क़वानीन फ़ितरत का बयान आम फ़हम ज़ुबान. So this is published in Pakistan, easily accessible. You can get it from the publisher. So this is a book which sort of explains many of these scientific ideas, including all these ideas that I talked about in this lecture. Turns out, in a language which I mean, this book is written not for physicists; it is written for any interested reader. That's all, and with no background in physics or mathematics, but you can really understand all these ideas and much more in this book. And very recently, last month, I wrote a very different kind of book, and this is called Mustaqbil Ke Khwab, and the subtitle is Kya Science Zindagi aur Kainat ke Raaz Hai Sarbasta se Parda Utha Sakegi. So it addresses some of these questions that we think about, but we don't know the answer. What is life? What is death? What was the purpose of our life? And so on. What will be the end of this universe? Why the universe is like what it is? It could have been very different, etc., etc. So these are the kind of questions that many of us think about. So I have tried to analyze it sort of from a scientific point of view. So this is something which was published just last month. So with that, I think I come to the conclusion of my talk, and I am really grateful for your attention, and particularly Dr. Saab for inviting me to give this and give me this opportunity to address this wonderful crowd that is here. Thank you very much.
Audience, do you have any questions?
Sir, I have a question. Sir,
Yes, please.
what is the difference between quanta, atoms, and the photon? Common. The quanta of light and photon.
Well, as a matter of fact, it's the same thing. Einstein introduced this motion in 1905, and if you look at his paper, he always used the term light quantum. It was 20 years later that somebody came up with this terminology called photon. So Einstein, till the end of his life, used the word light quantum to describe I mean, again, it is, as you know, it's a very strange concept. Yesterday, the talk at Karachi University, I mentioned how strange this concept is. And just to give you Einstein's, I mean, just to indicate how strange quantum mechanics is, I think in 1954, just 1 year before he died, he basically mentioned that all my life, for the last 50 years, I tried to understand what light quantum is. Today, every rascal thinks that he knows the answer, but nobody does. So yeah, it is a very strange concept, but it is the same thing. Yes.
So do you have
Yeah,
another
there was a question here. Yeah. Okay, please. Yeah.
Assalamualaikum, sir. It's been such an honor to have you here. I'm Vania Mansoor, first year, and I've been always interested in physics since a very young age. And because the thing you gave us today is precious, and I have so many questions. I've picked out three of the most I'm curious about. The first one, we've always studied that light carries information. We've always studied that from the very beginning. But in your discovery, what you discovered, you just said that light, no photon exists, right? The free communication, direction-free measurement, right? So do you negate the fact that light does not carry information and that the medium is the information?
Okay. Okay. What basically I said, okay, so in this particular case, it is information transferred through light photon. And if we go back to what I talked about, this photon is sent by Alice and it is detected by also Alice. But it turns out that the choice of the detector, whether it is detected at this one or this one, that depends on what Bob is trying to send by putting his hand in front or not putting it in front. So the point is that in this case, in our protocol, the information is sent through this process of sending a photon, blocking the photon or not blocking the photon, but the photon is always there. So it is not that we are doing a transmission without photon. The photon is there, but it is not in the public channel. That's all. So, but somehow it bounces back and forth through the system and gives us a click here or there, depending upon what is being done there.
Secondly, sir, the second one is that Einstein's famous saying, God does not roll dice. We've all heard of that. God doesn't roll dice. So this means that he does not believe in probability. He believes in, descriptive thing. No probabilities exist. But in quantum systems, we deal with probabilities. It's all about probabilities. What's your take on that?
So again, I wish you were there in the talk yesterday because then we discussed how many of the audience here was there in my talk yesterday.
2, 3, and 4, and 5.
Okay. So yeah. So I mean, this was basically the theme. I mean, the point is that just think of this very simple system, the beam splitter. Just this beam splitter. So the photon is coming in, and then either it is reflected or transmitted. And this is completely probabilistic. Either it is reflected. If we try to answer to this question, whether it will be reflected or transmitted, quantum mechanics does not allow us to speculate. It is completely probabilistic. Einstein was very unhappy about that. And he thought the role of science is to give us a definite answer, like Newtonian mechanics does. If I throw an object on the wall, and I know all the forces acting upon it, then I can predict with absolute certainty, according to Newtonian mechanics, where it will land on the wall. But if I take a quantum object like an atom or an electron and throw it on the wall, quantum mechanics gives me the answer probabilistically. It just tells me what is the probability that it will hit a particular point on the wall. So there is no definite prediction as far as quantum mechanics is concerned. Einstein was very unhappy about that, and I discussed in great details yesterday about what happened. And it turned out that eventually it was shown with the developments that took place in 60s and 70s that Einstein was proven wrong in that debate. He turned out to be not correct. And the results came out, fortunately for him, but after 10 years after his death. So, no, I think Einstein was very uncomfortable. I mean, it is actually a very paradoxical situation that some of the founders, and Einstein was one of them, and Schrödinger, like Schrödinger's equation defines everything. Both of them were very unhappy with what they had invented. And Schrödinger is quoted as saying that if I knew what it leads to, then I would not have involved in this whole business of quantum mechanics. So yeah, so Einstein basically argued that he doesn't think that God would play dice in the sense that he will give us a probabilistic answer, whether it will have the proton will go this way or that way, the probability. The answer should be a definite answer.
Sir, in BB84 protocol, if we increase the number of bases, like right now we are using 2 bases, diagonal and horizontal and vertical, or if we reduce the bases, like we work on a base, single base, is it effect on the result from result if we increase the number of bases for Alice and Bob? Right now we are using 2 bases. That is
The basis always consists of mutually perpendicular,
yes, that
exclusive possibility.
If we increase the bits, like
Because if you say only one, then it is a certainty. You just have
yes,
one possibility.
if we will talk about we'll use different bases for Alice. Like right now we are using 2
Yeah,
bases.
yeah.
What will happen?
Okay, so I mean, as I explained, I mean, one basis is this,
Yes,
and the other basis is this rotating basis. And if you know the answer in this one precisely, then it becomes completely uncertain in this basis. And that was the essence of Bohr's principle of complementarity, something which Einstein argued against. If you know the history, this Bell's inequalities business and so on, for which 2022 Nobel Prize was given. So it was. Yes.
Assalamualaikum, sir. Sir, I have two quick questions which are compensating each other. One is, I've seen that people are doing quantum computing or quantum optics without having given a basic course in quantum mechanics. So, how important do you think to be expert in quantum mechanics is to further pursue quantum computing? And second question is, how important do you think is to get review for the original papers like EPR, Bell on locality, or Arnav form theory? Are they obsolete or still they worth reading?
Okay, so let me answer your first question by telling you an episode. So at my university, they were trying to hire a very famous quantum computing person from Berkeley to join our faculty in computer science. I'm in physics. So it turned out that for the interview trip, he was to be given a dinner, and since I worked in quantum computing, so these computer science guys invited me for dinner. So I went for dinner with them. And I asked precisely this question from this candidate, who was already a very famous person in the field. I said, where did you learn your quantum mechanics? And the answer stunned me. I was amazed with the answer. And he said, I don't know any quantum mechanics. And then I pursued. I said, and how did you? So it turns out that there are some aspects of quantum computing, like linear algebra. So what he knew very well was linear algebra. So what that meant was that he would understand all these protocols in terms of this binary logic that comes with the linear algebra, and that was sufficient for him. But if you really want to become a quantum computing expert, I think you should know the basic ideas. And in my very, very heavily biased opinion, the best book is So, and coming to your second question, what was the second question?
Second question was, how important is to read the original papers like EPR and Bell on locality?
As a matter of fact, I teach this course on quantum mechanics for the freshman students just coming out of high school. And I tell them that in this course you will really do some very novel things which nobody expects you to do in any other course. And one of the things is I assign them reading assignments. And it turns out that these original papers, particularly by Einstein on this EPR paradox, please go and read it. It's one of the most readable papers and very significant. Historically, it is one of the most important paper of the 20th century compared to that. So, I mean, the thing is that I think you should try. I mean, I mean, Einstein's paper is very transparent, but the reply of Niels Bohr to Einstein's paper, which in some sense came out to be victor in that debate, Niels Bohr came out to be victor in that way. That is completely incomprehensible. So you have your choice, which one. So Bohr's paper I would not recommend you to read, but I would recommend you to look at. Because he according to Bohr, he would not like to write, as he put it, he would not like to express himself more clearly than he can think. So, and that's why he appears very ambiguous at moments. But it turned out that, yes, I mean, his arguments held the test of time. Einstein's arguments did not.
So what is the current status of quantum computing hardware?
Okay, so you ask a very delicate question. I mean, last year was this centennial of quantum mechanics, and I had the opportunity of giving some keynote talks on this subject. And it turned out that some other speakers came from the industry, people who are developing this hardware and developing things. There is one development about which I feel very, very concerned, and I expressed that in one of those forums. And that is that industry now has gotten into this area of quantum computing. They are spending millions, perhaps billions of dollars on this, on developing the hardware. And what hardware means is that they have this network of entangled systems which connect with each other and so on and so on. So that has been developed, like IBM has done it, Google has done it, and so on and so on. But the problem is, there is a big problem. When I do research in a university, it's not my responsibility for a device to come out of it. I mean, my job is to create new ideas and so on, and some of them are useful, some of them are not so useful. But industry, when it gets interested in a problem and expecting such huge amounts of money, someday they would like to get their money back. And my fear is that this quantum computing, where they have spent a very large sum of money, they have not yet come up with a single device that they could market. I mean, I talked to the big guys in IBM and Google and so on, they're point blank. So initially they would sort of try to wave their hands, but you try to nail them down. Please tell me what you can do with it, with the whole setup that you have done. And then they raise their hands and say, well, we are hopeful, but we haven't done it. And my fear is that very soon they will discover that it is not so easy. It's not so easy to come up with a specific device based on quantum computing. Quantum communication is a big success. The third part, which I did not talk about, quantum microscopy and lithography and so on, and I've done a lot of work on that. And for 10 years, that was what I was doing, trying to overcome these limits which were talked about by others. But quantum computing, I am very pessimistic. But it is my very, very personal opinion that maybe we won't see a device coming out soon. I mean, China, for example, invested a lot. I mean, in some sense in these areas, what China does, the United States want to mimic. They don't want to be left behind. And China now has realized this thing, and they have taken away this quantum computing projects from things like Alibaba and so on. And now they put it under the government where there is hardly any responsibility. Yes.
मैं एक तो आपकी जो किताब है क्वांटम मैकेनिक्स फॉर द बिगिनर्स उसके ऊपर एक कमेंट करना चाह रहा था अगर आप इजाजत दें। फर्स्ट ऑफ ऑल ये तो हमें बड़ा अच्छा लगा कि वी हैड yesterday lecture at Karachi University and we transited from fundamental quantum mechanics to the technology here. I'm really impressed again. ये जो किताब आपकी है जो पिछली स्लाइड में आपने दिखाया था क्वांटम मैकेनिक्स फॉर द बिगिनर्स, ये हम पढ़ाते भी हैं बच्चों को और इस वक्त जो दुनिया भर में भी यकीन तौर पर पढ़ाई जा रही है। एक और किताब है इसके साथ साथ जो बहुत पॉपुलर है और वो है इंट्रोडक्शन टू क्वांटम मैकेनिक्स बाय जॉन डेविड ग्रिफिथ। वो भी पॉपुलर बुक है शायद, लेकिन उसमें और इसमें थोड़ा सा जो फर्क है यानी ग्रिफिथ के साथ मेरी कम्युनिकेशन भी हुई है जब वो 2010 और 11 में उनको मैंने एक ईमेल किया था कि आप इसका जो फर्स्ट चैप्टर है, इनफैक्ट सेकंड चैप्टर जो है which doesn't start from the Schrodinger equations and heavily mathematics, तो मैंने उनसे कहा था कि आप इसमें पहले तो हम बच्चों को मोटिवेट करें, क्वांटम मैकेनिक्स की सरप्राइज जो एंटिटीज हैं वो उनको हाईलाइट किया जाए, बाद में फिर हम मैथमेटिक्स की तरफ आए। तो उनका जो रिप्लाई था वो बड़ा इंटरेस्टिंग था। ही सेड इसमें टू एस्पेक्ट्स हैं। एक तो ये है कि first everybody has to work on calculation and then move forward to understand it, जिसको लोग आजकल कहते हैं कि shut up, just calculate। मैंने उनको एक रिप्लाई किया था और मेरे ख्याल है कि आपकी किताब का वो लिंक है। उनको कहा था कि मेरा ये ख्याल है कि मेरा इससे ऑपोजिट ख्याल, पहले बच्चों को थोड़ा सा इस तरफ लाया जाए, इसकी जो सरप्राइजिंग एंटिटीज हैं उसकी तरफ हम उनको समझाएं, उसके बाद फिर मैथमेटिक्स होना चाहिए। और मेरे ख्याल है आपकी किताब को मैं देख रहा था, इसका जो श्रोडिंगर इक्वेशन आपने बिल्कुल लास्ट चैप्टर में रखा है और शुरू के जितने चैप्टर्स हैं उसमें आपने चीजों को इस तरह कोहेरेंस का आपने बार-बार जिक्र किया है।
नो कैलकुलस,
सुपरपोजिशन का आपने बार-बार जिक्र किया, which is the backbone of the quantum computers और क्वांटम कंप्यूटर। आपने नॉन लोकैलिटी को बहुत ज्यादा हाईलाइट किया हुआ है। तो स्टूडेंट की मेरी जो रिकमेंडेशन है कि ये इस बुक को यकीनी तौर पर देखें, इससे यकीनी तौर पर आप एक मोटिवेशन होगी, उसके फिर बात कैलकुलेशन करते रहें। यकीनी तौर पर क्वांटम मैकेनिक्स में कैलकुलेशन जो है वो बहुत इंपॉर्टेंट है। और आखिरी पॉइंट ये है कि क्वांटम कंप्यूटर्स के हवाले से इस वक्त मिसाल के तौर पर एज बीइंग अ फिजिसिस्ट स्टैंडर्ड मॉडल्स की जो प्रेडिक्शंस हैं और जो सर्न के अंदर जो डाटा अवेलेबल है उसमें जो सबसे ज्यादा उसकी कंपैटिबिलिटी में जो सबसे बड़ा मसला है वो ये है कि उसका जो कंप्यूटिंग टूल है वो बहुत वीकर है। आई थिंक इफ द क्वांटम कंप्यूटर becomes available, तो फिर मेरा ख्याल है कि नेचर की जो रियलिटी है शायद उससे हम बहुत जल्द आशना हो सके। दैट्स माय। इसके ऊपर आखिरी पॉइंट पे आपको कोई देख है प्लीज।
आई थिंक पहली बात तो ये है कि थैंक यू वेरी मच फॉर योर कमेंट्स एंड pointing out the basic idea behind this book. The objective of this book was in some sense convey the excitement about quantum mechanics and also emphasize how the significance of these laws. I mean, it's not like classical. I mean, it is against our intuition. That is the whole point. That quantum mechanics. The reason why I had to include Schrodinger equation, which requires the knowledge of calculus, was because I thought that if someday these students go out and say very proudly that they took a course in quantum mechanics, and somebody asks them, "Do you know Schrodinger equation?" and they say no, then they are ashamed. So I introduced this, but by that time they have some knowledge of quantum. As well as your other question is,
क्वांटम कंप्यूटर्स की जो अवेलेबिलिटी होगी तो हमारे स्टैंडर्ड मॉडल और सर्न का जो डाटा है,
so this is still a hope, and this is not yet materialized. mean, for example, even now, I mean, this is one of the big hopes that you will be able to do that, but still there is no protocol which shows how you will take that data and solve the problem. I mean, we are at that stage. So, I mean, since younger generation is present here, I might like to mention that quantum computing, there is a good news and there is a bad news. Uh, the good news is that the field, after a passage of almost 30 years, if I count it from Shor's algorithm, is still in its infancy. There are very few problems that can be solved on quantum computer. So there is an avenue for you to come up with new protocols to solve those problems. The bad news, however, is that so many people, very, very bright minds, have worked on it for the last 20 years. But again, don't be intimidated by that. For example, I gave you two examples of how some very, very simple ideas, like what our idea was, just using a beam splitter and nothing else, and we could, in some challenge, what people have believed for thousands of years with just that very simple idea. So don't be intimidated by that, but yes, I mean, there is that opportunity to come up with new protocols which quantum computer can do. I mean, right now there is a very big need to come up with some solvable problems on quantum computing. And right now, when you see this notion that quantum supremacy, as it is called, this is a completely artificial thing. You define a problem which quantum computer can solve much faster than on a classical computer, but you define the problem. So this is not a fair thing to say. A fair thing is that there is a problem, whether you can solve it or not. And that is, there we are still going forward.
Thank you so much, sir. Thank you so much, sir, for your insightful discussion. I would now request Chairman, Department of Computer Science, to please present a token of appreciation to Dr. Professor Suhail Zubairy.
So thank you very much, Dr. Zubairy, and all the respected guests from different universities, and the students and the distinguished faculty members, and everyone. I think there are so many people working in the area of quantum technology, and very few people working who belong from Pakistan. But out of them, there are very few people who are realizing the main challenge of like the hurdles, the barriers which we are facing to bring large number of students and the faculty into the area of quantum technology. And this is the work which Dr. Zubairy, what he is doing, that at one side he is doing very complex thing in the laboratory. On the other side, his contribution is to explaining things in a very simple manner. In Urdu language जो उन्होंने काम किया है, और ये हमारे लिए भी, हमारी अपनी क्वांटम लैब के अंदर हमें क्वांटम से रिलेटेड लोगों को अट्रैक्ट करना, उनको बुलाना, इट्स ए चैलेंज. लेकिन ये इस तरह के कॉन्ट्रीब्यूशंस, और फिर he came all the way from Texas, USA to Islamabad, then traveled to Karachi by his own. So this is a great contribution. I have no words to give him these. So thank you very much. Thank you very much for traveling all the way. I think now we will have a group photo with our respected guests, and then we will conclude the session. Okay, thank you very much.
Audience सारी यहाँ पे क्या